At this very moment, an object born under the light of another star, 3I/Atlas, is hurtling through our solar system at breathtaking speed. Its brightness doubles every few weeks, and it has spawned a massive green cloud stretching 500,000 kilometers across as it rushes headlong toward Mars. Astronomers anticipated a faint flicker in their telescopes. Instead, 3I/Atlas now blazes 6 times brighter than any prediction suggested, baffling observatories across Earth and igniting fierce scientific debate about what powers this extraordinary outburst. Is it a hyperactive nucleus releasing unprecedented amounts of material? Could sunlight be unlocking exotic ices forged in an alien star system? Or is something even stranger at work? With its closest approach to Mars just weeks away and Earth's viewing window about to slam shut as the comet vanishes into the sun's overwhelming glare, scientists face a race against time. Before 3I/Atlas speeds beyond our reach forever, what force drives this unprecedented celestial display? And what mysteries hide within that luminous shroud right now? Currently, 3I/Atlas sits approximately 2 astronomical units from the Sun, double the distance between Earth and our star, or roughly 300 million kilometers into space. Its velocity defies imagination. The comet tears the void at nearly 60 kilometers per second and continues accelerating with each passing day. When it reaches perihelion at the end of October, swinging closest to the Sun, that speed will peak near 68 kilometers per second. To grasp the sheer magnitude of this velocity, consider that it's more than double the speed of any planet orbiting our Sun. At this rate, 3I/Atlas could traverse the entire distance from Earth to Moon in just over an hour. Such extreme speed marks it as a true outsider, an object whose trajectory was shaped by gravitational forces far from our stellar neighborhood. On the astronomical brightness scale, 3I/Atlas has climbed to magnitude 12. This measurement might seem abstract, but it carries significant practical implications. The comet remains completely invisible to the naked eye, far too dim for casual observation. Even experienced amateur astronomers require at least a medium-sized telescope to detect it, and success demands perfectly dark skies far from city lights. The difference between magnitude 6, the threshold where the human eye can just barely detect an object, and magnitude 12 represents a factor of roughly 250 times fainter. Yet despite these observational challenges, the comet's apparent brightness has been increasing at a pace that shattered every predictive model. The coma, that vast cloud of gas and dust enveloping the hidden nucleus, has expanded explosively. Recent measurements indicate it now spans several 100,000 kilometers, rivaling the diameter of Jupiter itself. This dramatic expansion serves more than visual spectacle. It fundamentally explains why telescopes detect far more light from the comet than anticipated. As the coma balloons outward, increasingly vast amounts of sunlight get reflected and scattered by its particles, amplifying the object's measured brightness, even while the solid core remains concealed at its heart. Every major survey telescope and professional observatory tracks these critical numbers with intense focus. The Atlas team, who first detected the object during their automated sky patrol in early July, logs each new position and brightness measurement in real time. These observations feed sophisticated trajectory models and trigger immediate alerts to the minor planet center whenever sudden changes occur. With both the Mars flyby and perihelion rapidly approaching on the horizon, these hard metrics, distance, speed, and brightness, establish the essential baseline for everything that follows. In September, 3I/Atlas defied every expectation with a dramatic surge in brightness that caught the astronomical community completely off guard. The light curve, the chart astronomers use to track how an object brightens or fades over time, veered sharply away from its predicted path. This wasn't a subtle deviation or minor adjustment to the forecast. It was an abrupt, violent departure that triggered a cascade of debate across professional observatories and amateur astronomy networks alike. At the center of this puzzle lies the comet's coma, that vast and continuously expanding cloud of gas and dust surrounding its hidden nucleus. As the coma grows larger, it reflects and scatters increasing amounts of sunlight, causing the entire object to appear progressively brighter when viewed through telescopes. But the rate of this brightening exceeded all reasonable expectations, suggesting processes at work that current comet models don't adequately explain. By early October, the the window for observing 3i/Atlas from Earth began closing rapidly. Each evening, the comet sinks lower into twilight, pressed inexorably closer to the sun's overwhelming glare. The angular separation between 3i/Atlas and the sun, what astronomers call solar elongation, will shrink below 30 degrees by October 21st. That critical threshold marks the point where even the world's largest ground-based telescopes struggle to separate the comet's faint light from the overpowering brightness flooding the sky. For most observers around the world, the practical viewing window has already narrowed to a razor-thin sliver of time immediately after sunset, with the comet barely clearing the horizon before vanishing into atmospheric haze. Amateur observation networks scramble desperately to capture the last usable images. Online astronomy forums filled with reports of failed attempts mix with rare successes, as observers wage a losing battle against encroaching twilight. Some coordinated teams launch global campaigns, creating observation relays that hand off duties from one longitude to the next, hoping to squeeze out just a few more precious frames before the conjunction blackout begins. Professional observatories, bound by stricter safety protocols designed to protect their sensitive and expensive optics, have already begun pulling back from the chase. The risk of damaging delicate equipment by pointing too close to the sun is very real, and few institutions are willing to take that chance with their instruments. The urgency transcends merely lost photographs or missed imaging opportunities. Once 3i/Atlas passes behind the sun from Earth's perspective, there will be a complete data blackout. No direct measurements possible, no spectra to analyze, no method to track changes in brightness or structural evolution. For astronomers, this means every remaining observation before October 21st becomes absolutely critical. The geometry of the solar system itself is shutting the door on Earth-based observations, and the comet will slip out of reach precisely as it approaches its most active phase near perihelion. The only hope for continued monitoring will come from observation platforms far from Earth's line of sight, a challenge that now falls squarely on the shoulders of spacecraft currently orbiting Mars. For a brief but crucial window, Mars becomes humanity's only outpost with a front-row seat to 3i/Atlas. As Earth-based telescopes go dark, swallowed by the sun's glare, scientific focus shifts dramatically to the fleet of robotic orbiters circling the red planet. Each mission brings a different set of capabilities to bear on this unprecedented opportunity. The European Space Agency's Mars Express carries a high-resolution stereo camera and Omega spectrometer, instruments capable of capturing both detailed images and chemical fingerprints from millions of kilometers away. The ExoMars Trace Gas Orbiter, equipped with NOMAD and ACS spectrometers, was designed to detect faint signatures of gases in Mars's atmosphere, but it can turn those sensitive instruments toward the comet to sniff out water vapor, carbon dioxide, and even exotic volatile compounds across 3i/Atlas's sprawling coma. NASA's MAVEN orbiter, built primarily to study Mars's upper atmosphere and how it interacts with the solar wind, can retune its ultraviolet spectrograph to catch emissions from the comet's gas and dust. Meanwhile, its plasma instruments stand ready to monitor how the solar wind, that constant stream of charged particles from the sun, interacts with this interstellar visitor as it passes through Mars's neighborhood. The Mars Reconnaissance Orbiter, famous among planetary scientists for its razor-sharp high-rise camera that captures stunningly detailed images of the Martian surface, possesses the potential to resolve 3i/Atlas's nucleus directly if conditions align favorably. Though tracking a fast-moving comet presents significant challenges for any spacecraft designed primarily to stare at a planet, the geometry favors Mars during this encounter. On October 3rd, 3i/Atlas sweeps within approximately 28 million kilometers of Mars, close enough for these orbiters to attempt direct observations with their full suite of instruments, yet far enough away to avoid triggering the dust hazard protocols that once severely hampered earlier comet flyby missions. Instrument teams have spent weeks running complex simulations, updating ephemeris files with the latest trajectory data, and negotiating for precious observation time slots in already packed mission schedules. Every team wants a piece of this historic encounter. The wish list is ambitious. Visible and infrared images to map the comet's structure and evolution, ultraviolet spectra to measure gas reduction rates and identify specific molecules, plasma data to probe how the comet's own atmosphere interacts with the solar wind, and perhaps most ambitiously, attempt to image the nucleus itself as a distinct point source separate from the sprawling coma. Scientists hope to chart the detailed chemical makeup of material being released as the comet heats up during its approach to the sun. No mission has promised uninterrupted coverage. Observation plans remain constrained by spacecraft pointing limitations, data bandwidth restrictions, and the unpredictable timing inherent in coordinating observations of a fast-moving target. But even a handful of successful observation passes could deliver insights impossible to obtain from Earth. Direct measurements of dust grain sizes and compositions, gas production rates, and plasma interactions at a scale and proximity never before attempted for an interstellar object. For now, the spotlight shines on Mars and its robotic sentinels. The science team stand ready to seize this rare opportunity before 3I/Atlas speeds onward toward its date with the sun. The first characteristic anyone notices about 3I/Atlas is its striking green glow, an eerie, almost otherworldly luminescence that sets it apart even in the telescope eyepiece. Spectral analysts quickly zeroed in on this distinctive color, carefully scouring the comet's light for chemical fingerprints that could explain the phenomenon. The consensus, backed by ultraviolet-excited spectra captured by both professional observatories and dedicated amateur teams, points to diatomic carbon C2 as the primary culprit. When intense sunlight strikes carbon-rich molecules drifting in the coma, it excites them into higher energy states. As these molecules relax back to their ground state, they emit vivid green light, particularly in the swan bands centered around 510 nanometers wavelength. This emission signature is considered classic for active comets, documented in many solar systems. Visitors. Yet 3I/Atlas stands out dramatically for the sheer intensity of its green hue, especially considering it's still located at a distance of 2 astronomical units from the sun. Not everyone in the scientific community agrees completely on the details, however. Some research teams have flagged possible contributions from ionized carbon monoxide, CO, or the cyanogen radical, CN, especially in the earliest spectra captured during September. Both of these molecular species can also produce green or blue glows when bathed in solar ultraviolet radiation, and spirited debates have erupted in peer-reviewed discussions over calibration procedures and the proper handling of background light subtraction in the data processing. Still, the most robust datasets, those with the cleanest signal-to-noise ratios and the widest spectral coverage, consistently demonstrate that C2 emission dominates the visible coma. The chemistry at work here represents more than just an interesting visual effect or a pretty color for photographs. The extreme velocity of 3I/Atlas means that solar radiation slams into fresh ices and pristine dust at an accelerated rate compared to typical comets, rapidly peeling off volatile molecules and mixing them into the expanding coma. As a result, the green color isn't merely a passive marker for carbon content. It serves as a real-time indicator of how quickly the comet's surface evolves and transforms as it races sunward. A growing number of sharp-eyed observers have begun noticing something distinctly odd about 3I/Atlas's appearance, a faint, spike-like feature that appears to stretch back toward the sun itself. This so-called anti-tail runs completely counter to what most people expect from comets, where dust typically gets swept away from the sun by radiation pressure, forming the classic tail that always point away from our star. In the case of 3I/Atlas, both geometry and physics are conspiring to flip this familiar script. When a comet races through the inner solar system at extreme velocities, as 3I/Atlas is currently doing, dust grains ejected from a nucleus can actually travel ahead of the comet along its orbital path, especially if those grains are large or carry an electrical charge. From Earth's perspective, given the right viewing angle, these forward-moving particles can project a slender spike pointing sunward, an anti-tail visible only when the alignment between Earth, the comet, and the sun hits a precise sweet spot. Plasma physicists studying the phenomenon point out that the rapid expansion of the coma, combined with the comet's exceptionally high velocity, creates an extraordinarily complex environment where electromagnetic forces can rival or even exceed gravity's influence on small particles. Charged dust grains caught between the relentless solar wind pressure and the comet's own outflowing material can be focused and channeled into narrow streams by these competing forces. These sunward features aren't permanent structures. They depend on the constantly shifting interplay of grain size distribution, electrical charge states, and the ever-changing direction and intensity of sunlight as the comet moves. The effect becomes amplified by the unique viewing geometry during late September, with 3i/Atlas's orbit placing Earth almost exactly in the plane of its dust sheet, creating the optimal conditions to see what would otherwise remain hidden. So far, reports of a sunward antitail on 3i/Atlas remain somewhat tentative and unconfirmed. Amateur observers and some professional teams have flagged possible hints of the structure in their images, but no peer-reviewed analysis or precise measurements have yet appeared in the scientific literature. The phenomenon itself isn't new to comet science. Antitails have been documented in rare solar system comets when viewing geometry aligns correctly, but its potential appearance on an interstellar object traveling at these extreme speeds represents something genuinely rare in the observational record. For now, the possible antitail adds yet another layer of intrigue to an already unpredictable visitor, offering tantalizing hints at the complex dust plasma physics playing out as 3i/Atlas barrels toward the sun. Every comet that visits our solar system brings its own peculiar characteristics and quirks. But 3i/Atlas stands out dramatically even among the rare company of interstellar visitors. The first two confirmed interstellar objects set the boundaries for what astronomers initially expected from such visitors. Oumuamua, discovered in 2017, arrived as a dry, cigar-shaped enigma. No visible coma, no tail, just a tumbling shard material that slipped through the inner solar system almost unnoticed except for its bizarre trajectory and mysterious acceleration. Its reddish surface and complete lack of typical cometary activity sparked intense debate about whether it might even represent some form of artificial object, though natural explanations eventually prevailed. 2 years later, 2i/Borisov arrived displaying all the hallmarks of a classic textbook comet. A bright blue-tinted coma, a well-developed dust tail, and a chemical signature dominated by water vapor and cyanide compounds. In many respects, 2i/Borisov resembled the icy wanderers born in our own solar system's distant reaches, objects that orbit the sun every few centuries after being gravitationally nudged inward from the Oort cloud. 3i/Atlas, however, refuses to fit neatly into either established category. Its coma isn't just large. It's unusually green, a result of strong diatomic carbon emission not observed at this intensity in most solar system comets. The brightness surge, nearly sixfold above predictions, has no parallel in either Oumuamua's muted passage or Borisov's steady, predictable brightening. And while Borisov's tail streamed away from the sun exactly as expected, 3i/Atlas hints at a sunward antitail, a rare feature familiar from only the most unusual solar system comets, but virtually unheard of in objects from interstellar space. Even when compared against recent spectacular solar system comets like C/2023A3, such as Atlas, which displayed their own dramatic burst of activity and captured public attention, 3i/Atlas occupies a class by itself. Its combination of extreme speed, unusual chemistry, and unpredictable behavior forces astronomers to fundamentally rethink the boundaries between comets formed in our solar system and those forged in the vastly different environments of distant planetary systems. For classification teams tasked with categorizing these objects, the challenge extends far beyond simply assigning a taxonomic label. Each anomaly in 3i/Atlas's behavior represents a potential window into physical processes that may have shaped small bodies throughout the galaxy. The stakes extend beyond academic curiosity. Every new measurement carries potential to overturn decades of carefully constructed assumptions about what it fundamentally means to be a comet and what stories these visitors can tell about the alien worlds and star systems they left behind. After perihelion, as 3i/Atlas swings around the sun and begins its outbound journey, it will almost certainly begin to fade, likely far more rapidly than it brightened. Most predictive models anticipate a sharp drop in apparent magnitude as the comet speeds away from the sun's warmth, its coma shrinking and dispersing back into the cold darkness of space. For anyone hoping to catch a glimpse during this phase, the observational requirements only become more demanding. A telescope with at least a 20-centimeter mirror becomes a practical minimum for detection, and even then, Only the most sensitive digital cameras, equipped with modern sensors, will capture more than a faint smudge against the star field. Visual observers attempting to spot it through the eyepiece will be completely outpaced by the comet's rapid retreat into dimness. Image stacking techniques, combining multiple exposures to build up signal, and careful background subtraction will become absolutely essential for tracking any lingering activity or structural changes as the comet fades. The practical side of comet watching during this phase shifts increasingly to online dashboards, coordinated observation campaigns, and citizen science networks. Some of these collaborative efforts are organized around Discord servers where observers share real-time updates, while others operate through platforms hosted by established astronomy organizations. These networks collect raw data from backyard telescopes scattered across the globe, process the images through shared analysis pipelines, and post updated light curves that anyone can follow from their computer. For many participants, this represents the first time a truly interstellar object's complete journey has been chronicled by amateur astronomers in near real time, from discovery through perihelion and into the fade. The scientific stakes don't diminish when the comet begins to fade. Every new data point, each carefully measured position, each light curve point, each spectrum captured, each disputed detection or non-detection, feeds into a much larger puzzle. How do interstellar comets behave as they pass through a solar system so fundamentally different from their birthplace? What can their chemistry, their dust grain properties, and their fading light teach us about the building blocks that shape planets across the galaxy? Do they follow the same physical laws and chemical processes as our homegrown comets, or do they reveal fundamentally different formation environments? The questions now extend far beyond professional observatories and academic research programs, inviting anyone with a telescope, a laptop, or even just burning curiosity to join the search for answers as 3i/Atlas slips back into the cosmic dark from which it emerged. With Earth-based observations vanishing after October 21st due to superior conjunction, when the comet passes behind the sun from our perspective, the October 3rd Mars flyby becomes humanity's last opportunity for close-range, multi-instrument observations before the comet reaches perihelion. No detailed mission schedules for the Mars orbiters have been publicly released yet, leaving frustrating gaps in our knowledge about what data we can expect and when it might become available. Compared to Oumuamua and 2i/Borisov, 3i/Atlas displays a fascinating and perplexing mix of comet-like behavior and deeply atypical characteristics that don't match existing models. What happens as it rounds the sun, its detailed composition, its fade rate and pattern, its structural behavior under maximum solar heating, will fundamentally inform future studies of interstellar visitors and potentially reshape our understanding of planetary system formation throughout the galaxy. For now, the true nature of 3i/Atlas remains an open scientific question, grounded in hard-won observational evidence, and awaiting its next close encounter with our instruments. As it speeds toward perihelion and then back out into interstellar space, this mysterious green visitor carries with it secrets from another star system, secrets that scientists race to unlock before 3i/Atlas disappears from view forever, leaving only data, debate, and wonder in its wake. October 29th arrives with unprecedented anticipation rippling to the global astronomy community. At precisely 14:23 Universal Time Coordinated, 3i/Atlas reaches perihelion, its closest approach to the Sun at 0.65 astronomical units, while inside the orbit of Venus. For 3 weeks, the comet has been invisible from Earth, hidden behind the Sun's blinding glare. The only witnesses to this crucial moment are spacecraft scattered throughout the inner solar system, their instruments trained on a visitor from beyond. The Mars orbiters deliver first. As data packets begin streaming back to Earth through the Deep Space Network, scientists huddled in mission control rooms across 3 continents hold their collective breath. The initial images from Mars Reconnaissance Orbiter appear on screens at NASA's Jet Propulsion Laboratory, and the room erupts in gasps. The coma has exploded over 800,000 kilometers across, larger than the Sun itself. But that's not what stuns the assembled scientists. The nucleus, finally resolved as a distinct object separate from its shroud, measures approximately 4.2 kilometers in diameter, vastly larger than predicted. More shocking still, the high-rise images reveal something no one expected. The nucleus appears to be actively fragmenting. We're watching it break apart, announces Dr. Sarah Chun, lead scientist of the observation campaign, her voice trembling slightly. 3, possibly 4 distinct fragments, each trailing its own mini-coma. The ExoMars Trace Gas Orbiter spectrometers paint an even stranger picture. The chemical composition flooding from 3I/Atlas defies every model of comet formation. Yes, there's water vapor, but in ratios completely unlike anything seen in solar system comets. The carbon monoxide to carbon dioxide ratio is inverted, suggesting formation temperatures far colder than the Kuiper Belt. Most startling of all, the NOMAD instrument detects complex organic molecules, benzene, toluene, even polycyclic aromatic hydrocarbons in abundances that make seasoned astrochemists question their instruments. This isn't just a dirty snowball from another star, mutters Dr. James Wu, reviewing the spectral data at ESA's Operations Center. This thing formed in an environment we don't fully understand. Maybe around a different type of star, maybe in a molecular cloud with chemistry we've never modeled. MAVEN's ultraviolet spectrograph captures the comet's interaction with the solar wind, and the plasma physics team discovers their own surprise. The fragmented nucleus generates not one but multiple magnetospheres, mini-magnetic bubbles where 3I/Atlas's outgassing atmosphere deflects the solar wind. The boundaries between these regions flicker and dance, creating a light show invisible to human eyes but spectacular in ultraviolet wavelengths. November 2nd brings a development everyone feared and hoped for simultaneously. As 3I/Atlas emerges from behind the sun, now visible again from Earth's southern hemisphere, amateur astronomer Maria Rodriguez in Chile captures the first post-perihelion image from Earth. She immediately notices something wrong. The coma looks shredded. She posts to the Global Observation Network at 3:47 a.m. local time, her hands shaking as she uploads the image. And I'm seeing multiple brightness peaks instead of one central condensation. Within hours, professional observatories confirm her observation. The comet hasn't just fragmented. It has shattered into at least 7 distinct pieces, each following a slightly different trajectory. The largest fragment, designated 3I/Atlas A, retains about 60% of the original nucleus. The others range from house-sized chunks to kilometer-wide pieces, all embedded in a vast, irregular coma that now stretches across 15 degrees of sky, 30 times the apparent diameter of the full moon. The fragmentation transforms 3I/Atlas from a mystery into a revelation. As the broken nucleus exposes fresh interior material to sunlight, spectroscopes worldwide capture data from material that has remained frozen since this object's formation billions of years ago, in a planetary system perhaps hundreds of light years away. Dr. Chen's team works around the clock analyzing the data. The interior chemistry is even more alien than the surface, she explains during an emergency press conference at the International Astronomical Union. We're seeing isotope ratios that don't match solar system norms. The deuterium to hydrogen ratio suggests this comet formed in a region of space with different chemical evolution than our own solar neighborhood. We might be looking at material that formed not just around another star, but in another part of the galaxy entirely, a region where stellar metallicity and radiation environment produce building blocks fundamentally different from what created our own planets. As November progresses, each fragment's unique behavior begins telling its own story. Fragment 3I/Atlas C, one of the smaller pieces, suddenly brightens dramatically on November 8th, surging to magnitude 9, visible in good binoculars for the first time. Spectral analysis reveals an unexpected burst of nitrogen-bearing compounds, ammonia, molecular nitrogen, and even traces of amino acids. It's like each fragment is a chapter from a different part of this comet's history, explains Dr. Wu, coordinating observations from multiple ground-based telescopes. Fragment C must have been more deeply buried, more pristine. We're literally seeing billions of years of chemical evolution written in these breakup pieces. The plasma physics teams discover something equally profound. As the fragments spread out, each trailing its own ion tail, they create an unprecedented natural laboratory for studying how small bodies interact with the solar wind. The multiple magnetospheres documented by MAVEN now interact with each other, creating a web of magnetic field lines and plasma structures never before observed. Graduate student papers will mine this data for decades. But the biggest surprise comes from an unexpected source. On November 15th, the Solar and Heliospheric Observatory, SOHO, a spacecraft positioned between Earth and Sun to study our star, captures something extraordinary in its coronagraph images. Fragment 3 I/Atlas b, in the final moments before solar heating vaporizes it completely, releases a burst of dust that catches sunlight in a distinctive pattern. Particle physicists analyzing the scattering signature realize they're seeing something unprecedented. The dust grains have a different crystal structure than any solar system material. The silicate minerals have a formation signature consistent with conditions around an M-dwarf star, a cool, red sun vastly different from our own. For the first time, scientists possess direct physical evidence not just that 3 I/Atlas came from another star system, but specifically what type of star system. This changes everything, states Dr. Chen, reviewing the SOHO data with her team. We now know 3 I/Atlas formed around a red dwarf, likely in the habitable zone of that cooler star. The organic molecules we detected, the unusual ice ratios, the bizarre chemistry, it all makes sense now. This comet formed in conditions where liquid water might have existed on its surface when it was part of a larger planetary system. We're not just looking at a comet. We're looking at a fossil from a potentially habitable world. By December, 3 I/Atlas, or rather, its fragments, begins to fade as predicted. The largest pieces move outward past Earth's orbit. Their coma is shrinking as they leave the sun's warmth behind. Some fragments will remain detectable for months, even years, as they journey back toward interstellar space. Others have already vanished, either completely vaporized or broken into pieces too small to track. But the scientific legacy is only beginning. The data collected during those frantic weeks represents a treasure trove that will reshape our understanding of planetary systems across the galaxy. Every spectrum, every image, every measurement tells part of the story about how worlds form under different stars, in different chemical environments, with different building blocks. The organic molecules detected in Fragment C spark intense interest from astrobiologists. If such complex chemistry can form naturally around other stars, the building blocks of life might be far more common than previously imagined. The unusual ice ratio suggests that the delivery of volatiles to planets, the water and organic compounds that make world habitable, might follow vastly different patterns in other stellar systems. The fragmentation event itself provides unexpected insights. Comet nuclei, scientists realize, may be far more fragile than anyone suspected, especially interstellar wanderers that have endured millions of years traveling to the galaxy's radiation environment and temperature extremes. This fragility has profound implications for theories about how organic compounds and water might be delivered to planets. Perhaps many more interstellar visitors fragment and vaporize completely, their chemistry mixing invisibly into the solar system's background rather than remaining identifiable as distinct objects. For the thousands of amateur astronomers who participated in the observation campaign, 3 I/Atlas represents something more personal. Maria Rodriguez, the Chilean amateur who captured the first post-perihelion images showing the fragmentation, becomes something of a celebrity in astronomy circles. Her images appear in scientific papers and news articles worldwide. I almost didn't go out that night, she admits during an interview with a science journalist. It was cold, I was tired, I had work the next morning. But something made me set up the telescope, and then I saw it. This thing that had traveled maybe tens of thousands of years from another star system, and I was the first human to witness that it had broken apart. I started crying right there in my backyard. It's the most incredible thing I'll ever see. The Discord servers and online observation networks that coordinated the global campaign have created lasting connections. Astronomers in Chile hand off observations to colleagues in Australia, who pass the watch to teams in Asia and Europe in an around-the-world relay that continues for weeks. Strangers become friends, united by their shared pursuit of knowledge about this visitor from the stars. Professional astronomers find themselves humbled by the dedication and skill of amateur observers. Dr. Wu later writes in a Nature commentary, "This was astronomy at its finest, a true collaboration between professionals with access to spacecraft and advanced instruments and dedicated amateurs with passion, skill, and telescopes in their backyards." Some of the most important data came not from billion-dollar space missions, but from observers who lost sleep and ignored their day jobs to chase this comet across the twilight sky. Science at its best is a collective human endeavor, and 3i/Atlas proved that once again. As 3i/Atlas fades from view, speculation already begins about what comes next. Statistical models, updated with lessons learned from 3 interstellar visitors, now predict that perhaps 1 or 2 such objects pass through the inner solar system every year. We simply haven't been looking carefully enough to spot them all. The Atlas survey, having discovered its namesake comet, receives renewed funding and expands its network of robotic telescopes. Other sky surveys follow suit, implementing algorithms specifically designed to catch the telltale motion of interstellar interlopers. The next generation of space telescopes, including those planned for launch in the coming years, incorporates dedicated observation modes for rapid response studies of newly discovered visitors. Dr. Chen's team proposes an ambitious mission concept: a spacecraft specifically designed to intercept interstellar objects, equipped with instruments to analyze their composition in situ rather than from millions of kilometers away. Imagine if we could have sent a probe directly to 3i/Atlas, she explains to a packed auditorium at an international conference. We could have sampled that alien chemistry directly, maybe even returned samples to Earth. We have maybe a decade to build and position such a spacecraft before the next really interesting visitor arrives. This needs to become a priority. The proposal gains traction. Space agencies across the globe begin preliminary studies. The idea of a standby spacecraft, ready to launch on short notice when telescopes spot the next Oumuamua or Borisov or Atlas, transitions from science fiction to serious planning documents and budget proposals. But perhaps the most profound impact occurs not in scientific journals or mission planning documents, but in the collective human consciousness. For those who followed 3i/Atlas's journey, whether professional scientists, amateur astronomers, or simply curious people reading news articles, the comet represented something transformative. For the first time, humanity didn't just theorize about other star systems or imagine their planets and moons and comets. We witnessed actual material from another stellar system, touched, however briefly, by our sun's light, studied by our instruments, photographed by our telescopes. The universe suddenly felt smaller and more connected. If comets from other stars visit our system, then surely our sun's comets must occasionally wander into other stellar neighborhoods, carrying perhaps traces of Earth's own chemistry out into the galaxy. We're not isolated, reflects Maria Rodriguez during a stargazing event at her local astronomy club months after the encounter, pointing up at the Milky Way stretching across the dark Chilean sky. That comet came from out there somewhere, maybe from a star we can see tonight, maybe from one too distant or too dim to make out. But it came here, and we saw it, and we learned from it. And someday, millions of years from now, maybe something from our solar system will visit theirs. We're all connected by these wanderers, these messengers from other suns. In the end, 3i/Atlas delivered more than data and scientific papers. It delivered a vision of the galaxy as a place of exchange and connection, where material and chemistry, and perhaps even the building blocks of life itself, wander between the stars, mixing and mingling across light years and eons. The comet arrived as a mystery, fragmented into revelation, and departed leaving behind not just answers, but better questions. Questions about how planetary systems form, how chemistry evolves across the galaxy, and what other wonders might be sailing through the darkness between the stars, waiting for humanity to look up and notice. The fragments of 3i/Atlas continue their journey outward, growing dimmer with each passing week, eventually dropping below the detection threshold of even the most powerful telescopes. By spring, they will be gone, indistinguishable from the countless faint stars that fill the sky. But they carry with them a piece of human curiosity, a moment when our species looked up and saw not just a comet, but a messenger from the larger universe, and we listened to what it had to say. Somewhere out there, perhaps, another civilization on another world orbiting another star might someday receive their own interstellar visitor. Maybe it will be a fragment of comet broken off from our Oort cloud, carrying frozen water from Earth's ancient oceans, organic molecules from our planet's early atmosphere, dust grains forged in our solar nebula. And maybe, if they're watching their skies as carefully as we watched ours, they too will learn that they are not alone, that the galaxy is filled with wanderers, and every star system is connected to every other by these ancient travelers. 3 I/Atlas came from the stars, blazed briefly through our sky in a spectacular display of fragmentation and discovery, and returned to the stars. But the story it told, the story written in its green glow, its bizarre chemistry, its fragmented nucleus, and the traces of its distant origin, that story remains here with us, expanding our understanding of the cosmos and our place within it. The mystery is solved. The visitor has departed, but the wonder remains.